Here's how we'll start today. This is lesson 6-4, so don't be alarmed by this, but I'm going to say that we got ourselves a big old basketball tournament. A lot of people know about March Madness. In your lifetime, you may have never experienced the fact, oh, can we wait on this? We could have never really experienced the fact that there should be 64 teams in this tournament. They've opened it up in recent years to have 68 teams because they have some play-in games. But let's say that we have ourselves a big basketball tournament where there's 64 teams in it, right? So I'm going to do this with this chart right here. This is round 0. How do you feel that there are 64 teams in there? And did you see it plotted this dot right here at 0, 64? Are you with me on that? Cool. Then they got to play each other, correct? Would you believe in a basketball game, even if you know nothing about basketball, right? Somebody's got to win and somebody's got to lose, correct? How many teams advance when we start with 64? Shouldn't, like, 32 of them survive. So after one round of play, would you believe that this dot now shows up, correct? Then the next weekend or maybe a few days later, they play again, right? There's 32 teams in this tournament. Somebody's got to win. Somebody's got to lose, right? So how many teams survive? And if you are familiar with March Madness, we call that the Sweet 16, right? You know. Then a couple days later, maybe a weekend happens, right? You know, 16 teams survive. They got to play. How many will advance? The Elite 8, right? You know, so do you see the dot being plotted here also, right? Then we go a whole other thing, right? And then how many teams will survive out of the 8? The final 4, right, you know, and then the final 4 happens, right? How many teams survive? 2, and then there should be like even another round after that, the 6th round. Those 2 teams play, called the championship game, and how many teams survived? 1, the winner, right? Should we have another round? No, because it wouldn't make sense for like a decimal to start showing up in this real life scenario. Here's the cool question. When I make a graph of this, is this linear? Like if I connected the dots, would it make a line? Yes or no? What do you think? Make a line? Zoom out a little bit on it. Or is it curved? It's definitely curved. This is our first experience of the year, right, to where we haven't graphed anything that's not a line in this case. Let's see if we can figure out a formula for this guy. I'll definitely help you, right? But could you tell me the basics? What happened to these numbers every time? Did they go up or down by the same amount? What do you think? Did they go up? Like, what did this one go down by? It went down by 32. Did this go down by 32 again? Nope. See, that would be a linear case if it goes up or down by the same amount every time. Not happening, right? What happened? Tell your neighbor. What do you think? Tell me. What do you think? What happened? Divide by 2 or multiplied by? Starts with an H. A half, right? You know, dividing by 2, multiplying by half, same thing. Would you believe half the teams survive all the time, right? So check it out. How many teams did we start with? So watch this. I'm going to graph this guy, y equals, and then this guy right here, this 64 is how many we started with. But you said like half the teams survive, so are you okay with me putting the 1/2 right there? And then look at this. You know how we've been dealing with exponential stuff? Look where I'm going to put the x. I'm going to put the x up in the exponents in that case. And did that connect the dots together, right? Now, realistically, it makes no sense to connect the dots together because you can't have like 1.5 rounds of basketball, you know, 2.3 rounds of basketball. You can't have, you know, like, oh, there's like 36, I guess, yeah, 36.5 teams survive, right? So like getting rid of the dots doesn't really make any sense, or they should only be dotted. But I wanted you to see, look what happens right here. Look at that guy. What does he get closer and closer and closer and closer and closer to? He gets closer and closer and closer to the x-axis, right? So would you believe that is like also the number 0 as a y value? It's going to get closer and closer to 0. That's called an asymptote. That's a weird word, an asymptote. So what we just saw was an exponential function. Here's what we got, dude. There's very important parts to this exponential function, but my job to really make sure you understand what's going on today is how do you know a function is exponential? Where should x be? Please say the exponent. Where should x be? In the exponent. But the weird thing is you got these other dudes right here. You've got this b for base and a for this a value. Going back to this guy, are you cool that in my formula right here, I do have x up in the exponent, correct? The base is 1/2, right? And then this, just like a value is 64, that's kind of like, in general terms, how much you started with. Are you with me? Didn't we start with 64 teams in this tournament, right? It's kind of like how much you started with. But the main thing is, why is it exponential? Because the variable x is up in the exponent, and who's the base? It goes back to some old Megan Trainor. It's all about that base, about that base, about that base. You're going to find that true about this lesson. It's lame, but it's true. So check this guy out. Is this equation right here exponential? Or in other words, is x up in the exponents? Yes. The base is who's got the x on it for an exponent. Are you cool that that base right there is a 3? Are you with me on that? So what I'm going to do just for fun is kind of show you what happens if I graph that. I'm going to clear all this out. Boom. And just make that is y equals 3 to the x. Hey, just out of curiosity before I delete this, would you say that this situation was like growing or decaying? You know, like we started with 64 teams. Did it grow or did it get smaller? It got smaller. That's like an exponential decay because that base in this case was 1/2. I'm going to make this 3 for the base. Look at this guy. Started at 1. Then doesn't it just like kind of take off real slow and then grow real fast? Would you call that exponential growth or exponential decay? Exponential growth. We are old enough still to remember COVID, right? You know, it's like it was a horrible time, but didn't that disease kind of start growing really slow, and then all of a sudden, holy cow, it went through the roof, and like the world, it took over the world, you know? That's an exponential situation, right? Exponential growth in that case. So how do you know if it's exponential growth or exponential decay? Well, I always say Megan Trainor tells you, right? It's all about that base, right? This base is bigger than 1. Let's fill out this table and graph this guy first, and here's what I want to do. I want to start right here. I don't care for those negatives right now. I don't care for those negatives. Let's put 0 in for x, and I'll bet we can do a lot of this without a calculator. Wouldn't this really be 3 to the 0th power? What's anything to the 0th power, baby? It's 1. So are we okay with putting a 1 right there in that spot? Then if I put 1 in for x, I'm going to just start over. I'm going to take 1 and substitute in there. Wouldn't that say 3 to the 1st power? Are you with me on that? What's 3 to the 1st power? That's 3. And then the last one of these would be 3 to the 2nd power, right? Because we put 2 in for x. What's 3 to the 2nd power? That's 9. Can you see that it went times 3, times 3? Like the next one would turn out to be 27. You know, it would be times 3 again, all that. But check this out. We got a little experience with negative exponents. This one would be 3 to the negative 1st, right? But doesn't the negative exponent like reciprocate the base, right? So would that be the same thing as this, 1/3 to the positive 1st in that case? What's 1/3 to the positive 1st turn out to be? 1/3. And then one more. I've got 3 to the negative 2nd is what I would do. Well, the negative exponent is supposed to reciprocate that base, so I'm going to do it over here. The base was 3. I reciprocated him, and he would be to the positive 2nd. What's 1/3 squared turn out to be? 1 squared is 1, and 3 squared is 9. Here's what I want you to look at. These. And just see how they relate to each other. How does 1/9 and 9 relate to each other? How does 1/3 and 3 relate to each other? Tell your neighbor an R word. They are what? Aren't those reciprocals of each other? Are you with me on that? So those are reciprocals. Let's graph these guys, right? So they've got a scale made up for us also. I'm going to start right here at 0, 1. Hey, bro, whoa, 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 watch ourselves. What are they counting by on our scales? Like right here is 4, right? And then here's 0. What would this tick mark right here be? It's got to be 2. So let's watch ourselves when we're plotting our dots here. Isn't 0, 1 like right there? Are you with me on that? So I plotted him. I'm just going to highlight them as I plot them. Boom, got him. Then I'm going to plot 1, 3. Hey, is this tick mark right here at 1? Is that correct? Is that 1? Yeah, so 1, 3. So here's 2. Wouldn't 3 be right there in between 2 and 4? And then 2, 9. Boom, 9's like right there. Those are the easy ones to plot because they weren't like the fraction-y ones. Are you with me on that? Then these other guys, you just got to guess, dude. Like there's no way to accurately be like where you're going to plot -1, 1/3. He's going to be like right there-ish, you know. I have no idea if that's perfectly where 1/3 is. It's just a guess, right? Same thing with -2, 1/9. It's just got to be a little bit lower, but here's why we did the little warm-up. Do you think these dots are ever going to get below the x-axis of y = 0? Or is there going to be an asymptote there? What do you think? Are they ever going to get down below? They're going to get closer and closer and closer and closer to it, but it would never, ever touch. So our job is to do this, is to graph this asymptote at the line y = 0. Take your straight edge, and please graph a dashed line. I want him to be dashed because it's kind of like it's imaginary, right? That line really doesn't exist. So I drew a little dashed line right here at y = 0, and I want you to write that equation right here, y = 0. And that'll help us connect these dots together, which is just a little freehand. It's going to get closer and closer and closer to that asymptote, but then as we go, it's going to get this exponential situation. It's just going to go through the roof, right? We'll put arrowheads on each one. Notice I actually made it go through the grid mark on that one, but that thing is going to take off, right? Like I said, if we did 3, y would turn out to be 27. If I did 4, y would turn out to be 81 after that. You know, it's just going to keep getting bigger and bigger and bigger and bigger. So homework's going to ask you a bunch of questions like this. They say b equals. I would rather you call that base, right? Like, so what is the base in this scenario? What's the base? How do you feel about 3? Is that okay? And then they're asking you, bro, is this exponential growth or exponential decay? You can tell just by looking, doesn't that grow as we go from left to right? So what do you think, exponential growth or exponential decay? So just circle growth. But here's the question, why? And we got to answer it in math terms. Homework might have it in English. You're always going to do it for me on paper in math terms. Here's why. It's because the base is bigger than 1. Like, that's in English. Hold on. Here's how we write it in math. Because the base is bigger than 1. How do you write the base? How do you feel about b? And then tell me, it's been a while since we had it. It was before break. Does that symbol right there mean bigger than? AKA greater than, right? Bigger than 1. If the base is bigger than 1, this thing's going to be exponential growth. And then this guy right here, this HA, stands for where is there a horizontal asymptote? My friends, as we learn through algebra, you can have vertical asymptotes. You can also have oblique asymptotes. That's way down the road for us. There is a horizontal asymptote. Don't just put 0. Isn't he at y = 0? Are we okay with that? Cool. Where did it start at? Where did it start at? What y value did it start at? 1, because that was the number right in front of the 3. Like, they didn't write it, but it's like 1 times this. Just like our other one, it started at 64. Didn't I have a 64 in front of there in that case? So that's exponential growth. Let's go to this guy right here. And you can tell me right now, boom, 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 boom. First of all, we have to ask, is it even exponential? Is x up in the exponents? Yes? Talk to me about that base. Bigger than 1? Nope, it is smaller, so our base is 1/4. Are we cool with that? Will this be exponential growth or exponential decay? Exponential decay. I know we're only circling the word decay. I do like us to say the word exponential in front of it because there's lots of kinds of decay situations. This is an exponential decay. Cool, so we'll get used to that. Why? It's not just about the base being less than 1. It's got to be like this. So the base is going to be between 0 and 1. How do you do that? Do you remember putting like b in the middle, and these two symbols, both as arrowheads, point to the left? The smaller number goes here, and the bigger number goes there. That's the mathy way to say the base is between 0 and 1. So here's what we've just kind of learned. For us to have an exponential growth or exponential decay, you can never have a negative number for a base, right? Because it's got to be between 0 and 1. You can't even have 0 for a base, and you can't even have 1 for a base. Are you with me? There's no equal to bars either. So the base, if it's bigger than 1, will be exponential growth. Exponential decay, it will be between 0 and 1. If a negative showed up, it wouldn't look like an exponential graph at all. It would be, the dots would be in way different places, right? So we'll see that later. So let's start right here, baby. This is where I like to start. If I put 0 in for x, what is 1/4 to the 0th power? It is going to be 1. Sorry, 1. It's going to be 1. Anything raised to the 0th power is 1. Cool? Then, if I put 1 in, what's 1/4 to the 1st power going to be? Anything to the 1st power is itself, right? So wouldn't you get 1/4 back on that guy? And then what's 1/4 to the 2nd power? Well, if you know what 1 squared is, and you know what 4 squared is, you know what 1/4 squared is, what would you get right there? 1/16. And you know what's cool about these guys right here is they shall be reciprocals of this guy. So even if I did it, this is like 1/4 to the negative 1st. Doesn't that negative exponent say, please reciprocate the base, right? The reciprocal of 1/4 is 4, and now I have a positive exponent, so shouldn't that be a 4 in that case? Or if you just saw this cool little pattern right there, hey, the reciprocal of 1/4 is 4, so who should this guy be? Who's the reciprocal of 1/16? 16. Are we cool with that? Let's plot these points right here. We've got ourselves, I'm going to save the fractions for last. Like, what order do I go in? I'm just saving the fraction-y stuff for last, right? So I'm going to plot 0, 1, boom. -1, 4. So that's like right there this time. And then -2, 16. And then I'm going to go plot all those weird fractions. So 1 1/4 is going to be like right here-ish. 2 1/16 is going to be right here-ish. And you see, like, if I connected the dots, just wait for me to connect the dots, it would do one of these scenarios. Isn't it still going to get closer and closer and closer and closer to 0? But instead of an exponential growth, it's an exponential decay in that case, right? So we'll take our straight edge and we'll draw that horizontal asymptote in right there. And we'll put him at y = 0. And those are the two plain Jane basic exponential guys. The first one we did was an exponential growth because the base was bigger than 1. The second one was an exponential decay. But they can really get weird on us. Let's see if they do that on the next one. Kinda. Something's different. Question, is this exponential? Is x up in the exponents? Yes. Which one of these is the base? The orange 0.5 or the red +3? Which one is the base? By the way, the base is the guy with the exponent on him. Which one's the base? The 0.5, right? Which we're pretty familiar with 0.5 being the same thing as 1/2. Are you with me on that? So what do you think? The base, we got him as 0.5. Exponential growth or exponential decay? Exponential decay, right? How come? I'll say it in English, you write it in math. Because the base is between 0 and 1. Because the base is between 0 and 1. So B goes in the middle. Symbols point to the left each time, 0 and 1. But let's hold off on that horizontal asymptote, because so far, hasn't it always been at y = 0? Are you with me on that? Something's different about this guy. What's different? There's a +3 involved with it, right? So what we have done so far on these other ones is we filled out these tables without a calculator at all. That's probably not the most likely thing. On this one, I think we should probably use a calculator. Does that sound okay? So grab ye old calculator, and let's do this. I'm going to start with 0, which a lot of people might think they really don't need to use a calculator, and that's awesome. But isn't it going to be 0.5 to the 0th? And then I got to get out of that exponent and hit +3. Are you with me on that? Just kind of punching in what I see, but where there was an x, I put a 0 in the case. So I got 4 back. See if that makes sense. What's 0.5 to the 0th turn out to be? isn't this the number 1, right? And then you added 3 to it. Are you with me on that? So it really became 4. But you're still welcome to use a calculator to punch these guys in. Are we cool with that? I'm going to do the same thing on the next one. I'm going to do 0.5 to the first, right? Which I bet our brains know that's 0.5, right? And if you add 3 to it, make sure you get out of your exponent to do it. Don't you get 3.5 back in that case? And I'm cool with us having decimals. It's like the first ones were fractions because it was just so plain Jane and easy. Decimals are totally fine, right? Totally fine. So let's do 0.5 to the second, right? And then add 3 to it in that case. And did you get 3.25, right? So that's not bad. The reason why we're definitely going to use decimals is because, yeah, it'll be pretty nice on these other ones that are going to come out really, 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 really weird. So 0.5 to the negative first, add 3 to it. And did you get 5 back? That's not a dirty number at all, but still, did you get 5 back on that one? Here's the weird part. People are like, whoa, Mr. Fonstill, whoa, 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 whoa. I thought those were supposed to be reciprocals. I need to add to my statement. The only time they were reciprocals is because back here was the number in front of this 1, yes or no, and they were adding nothing to it, right? That's really the only time that's going to come out so nice, right? So the reciprocal thing only works if it's just a basic Karen of an exponential kind of thing. Are we all right with that? So, okay, so, and then we'll do negative 2. So 0.5 to the negative 2 plus 3. I hit the wrong button. Plus 3. Did you get 7 back on that guy? Cool. Let's plot those points. Not too shabby. Negative 2, 7. Hey, they don't have a scale on it, so we have to create our own scale. Let's see if we can make it to our highest point, which is 7, by counting by ones. Do I have enough spots? 1, 2, 3, 4, 5, 6, 7, 8, 9. Do I have enough spots to count by ones, right? So that'll work. Nice. So we're going to do this. 1, 2, 3, 4, 5. Negative 2, 7 is like right there. Negative 1, 5 is like right there. 0, 4 is like right there. And then 1, 3.5 is like right there. And then 2, 3.25 is like right there. And with no mathematical experience on this like you guys have, you probably wouldn't be able to connect those dots together very successfully without knowing where the asymptote is. Our asymptote so far has always been at y equals 0. Are you with me on that? I'm going to give you a little cheat code because we are advanced students. Here's a cheat code. This number right here is always where the asymptote is, right? Instead of at y equals 0, because wasn't he 0 before, right? He's going to be at y equals 3, right? So y equals 3 is that guy, and we will graph that dude as a dashed line right there. I kind of missed a little bit, but I'm going to leave it y equals 3. And to just bring us into some serious advancements, because we're going to do this eventually anyway, this plus 3 took the whole graph, which starts right here. Do you see this thing on the wall? All of these guys are called parent functions. If these were ice cream flavors, they'd be vanilla, dude. They're as plain Jane as they could get. This is the most plain Jane exponential growth that you got right here. Isn't it horizontal asymptote at y equals 0? I don't care if it's exponential decay either. It's going to be at 0. That plus 3 will do this. He will shift the graph 1, 2, 3 units up, right? So like everything moved up 3 in that case is what really happens. Cool. Let's try another one of these guys. I like to answer these questions first. First, is it exponential? Yes or no? Is x up in the exponent? Yes. Who's the base? 5/4. Interesting question. Before I say exponential growth or exponential decay, is 5/4 bigger than 1 or between 0 and 1? You can punch it in your calculator if you don't know. If you did 5 divided by 4, you can see what kind of number you got back. Is 5/4 bigger than 1 or between 0 and 1? He's bigger than 1, isn't it? 1.25 as a decimal. If the numerator is bigger than the denominator, you're going to be bigger than 1 when you divide that out. So this is going to be exponential growth. Why? I'll say it in English. You write it in math. The base is bigger than 1. the base is bigger than 1. And let's see how much we've been paying attention on this Thursday right here. Can you tell me where the horizontal asymptote is going to be at before I graph anything? Where's the horizontal asymptote going to be at? Very close. I like that you said 2. We're still new at this. It's got to be at y equals 2. Like 2 is a number, y equals 2 is a line, right? So at y equals 2. I like it. I like it. I like it. So now let's use our calculator. Look at this. Not only did they have this thrown in there, you see we also have this wacky little dude in front of there as well. This is going to be a mess, right? So the calculator shall do the work for us. I'm going to just keep with my pattern and starting at 0. I'm going to do 2 times 5/4. How did I type in 5/4? I did 5 divided by 4 in parentheses, right? You know, just put it in parentheses. Raised to the 0th, and then plus 2. Are you cool that I have just typed everything down that I saw? Where there was an x, I put a 0 in its spot right there, right? So that's going to turn out to be 4 in that case. If you want to think of it like this, it was like this. 5/4 to the 0th is really the number 1. You know, this happened first according to the order of operations. There is a times 2 and then a plus 2. 2 times 1 is 2. 2 plus 2 is 4. I don't care that you do all that work. Can we punch it in our calculator and get the right numbers? So let's do 1. I'm going to do 2 times 5/4 to the 1st plus 2. Yeah. And did you get 4.5 back? 4.5, using a pen. Is this the last one, or is there another one after this? Okay, good. So we'll finish this together, right? So let's do 2 times 5/4 to the 2nd plus 2. Did you get 5.125? Don't round him off. Like, that's still a nice clean decimal, so we'll put him in there, 5.125. Is that right? Is that what we should get? Yeah, that's what I got. So now let's go and do -1. Things are going to start getting nasty. Let's see. That's not too nasty. 3.6. I'll leave him like that. And then 2 times, bless you, 5/4 to the -2 plus 2. Actually, none of those turned out to be nasty, so I'm going to write all those decimals down. But you know what I mean by when I say nasty? Like, it might fill up your whole calculator screen. Then you just round it to 1 decimal place if it comes out nasty, okay? If it comes out real nasty, round it to 1 decimal. Those are not nasty, right? So let's go ahead and plot these points. I'd still like to start here. That's just my personal opinion. 0, 4, 1, 2, 3, 4. 1, 4.5, so boom. 2, 5.125, so boom. And then -1, 3.6. -2, 3.28. Man, that's not very exponential looking. But it is still exponential, and we'll talk about why it just looks so flat here in a second. But to finish this graph off, why don't we graph the asymptote first as a dashed line? So that's going to be y equals 2. And he's still exponential growth, so we just got to kind of follow this curve pattern. You might want to have to watch me before we do this. Follow the curve pattern. And it's going to get closer to that asymptote as we go. It's going to grow more as we go. But, bro, that doesn't do much at all. I put 4 different plain Jane exponential growths. Is x up in the exponent on all of them, right? Is all the bases bigger than 1? Yes or no? Which one is the flattest looking one color-wise? Purple, red, blue, or green? Which one looks the flattest? The green, its base is 1.25, right? Which one looks the steepest, the one that grew the fastest? The purple one, its base is 7. because things are going to get multiplied by 7 every time. So it's like if there was one thing right here, then the next one would be 7, then the next one would be 49, then the next one would be 343, and I don't know what 7 to the 4th is in my head, but it's just like, holy cow, if you keep getting times 7, it's going to grow really fast. Here's the moral of the story. Even though they're all exponential growths, the closer the base is to 1, right? Because isn't that the rule? To be exponential growth, you have to be bigger than 1. The closer it is to 1, the flatter it's going to turn out to be, right? The flatter it's going to turn out to be. So isn't our base back here 1.25, right? Isn't it 5/4? Why is it so flat looking right here? Because that base is really, really close to 1 in that case. So let's try one more. I want to do this with you. Talk to me. Exponential, yes or no? Yes. Exponential growth or exponential decay? It's all about that base. What do you think? Exponential growth or exponential decay? Decay. Could you please fill out all of this first? Pause the video, give it a shot, see what you think. I got all those. Where's the horizontal asymptote at? Just one more time. Where's that going to be at? Y equals 1. Cool. Horizontal asymptote at y equals 1. Now let's fill out our table. Just give you a little time to do this. There'll be some tables. I also want to explain to you how you graph these on your computer, right? You know, on this last one. So we'll fill that guy out. I got 5 when I put a 0 in for x. Is that cool? And then 4. And then 3.25, did those come out okay? What did this -1 turn out to be? Was it actually repeating? Sorry, I didn't punch. Was it 6.333333333? So, okay, so we'll just round it. If you did 1 decimal place, that's fine. That's what I told you. I wrote down 2. And then was the other one repeating? Was it like 8.111111111, or was it just 8.11? Whatever. It's pretty darn close to 8.1. Is that all right? You know why that doesn't matter so much? It might matter on computer because they're going to accept so many decimals, so read how many they tell you to round to. But aren't we just roughly guessing where those are anyway when we put them on the graph? You know what I mean? So it's like, all right, it's pretty darn close. So we'll graph our asymptote first. Oh, by the way, this is how you have to do it on the computer. It tells you also, please graph your asymptote. When you start hovering over this, it's going to have a dashed horizontal line just like floating there. It's like you got to put the dashed horizontal line first, so wouldn't that be at y equals 1, right? You do that guy first. That's what you have to do on the computer. Then it's got like a little option down there. It should automatically be selected that it's an exponential growth. It's like one of these little dudes down here. Sorry, that, you know, you've seen that they've had like the line tool right here and all this. They'll have a little tool right here that looks like an exponential guy, right? You know, so it's all curvy like that. You have to plot this point first, right? So you'll have a table filled out before you do it. You have to plot that point first, 0, 5, 1, 2, 3, 4, 5. And then you just plot any other point on there. I'm not even sure if you have to plot that point first. I think that you do, but maybe it's just any 2 points on there. I'm not quite sure, right? So, but I think plotting the 0 value first, and then if you plotted like 1, 4, then it would like, boom, it would make the exponential curve for you in that case. But here on paper, we got to do it all. So, bada boom. And then you connect. And it's just going to get closer and closer and closer to that asymptote, but it will never, ever cross it. Just like I was getting closer and closer and closer to the closet door, but I will never, ever touch it. Sorry mine's so squiggly and wiggly, like my stylus just isn't cooperating very nice today. Try to make it smooth. It's not really all wiggly in that case, but it's nothing perfect. How do you feel cool? How do you feel about recognizing if it's 1, exponential, and 2, if it's exponential growth or exponential decay? Cool. So now let's see if they had a bunch of them graphed right here. Sorry, yours is not in color. Here's what I do. I'm going to just not be overwhelmed by this because it is overwhelming to see all of this at once. I'm going to look through these choices, right? And here's something that I'm looking for first. I'm just going to go find all the exponential decays. You know what I mean? Like out of all those choices, talk to me. Which ones? What am I looking for to see if they're exponential decays? It's the B word is all I care about. A, base, right? The base has to be what? Bigger than 1 or between 0 and 1? So not you. That's bigger than 1. Not you. not you. Shouldn't this one right here be an exponential decay, right? And shouldn't this one right here be an exponential decay? Now I can go over to the graph and see which ones are going down. Are you with me on that? So how do you feel about either B or K, right? Both of those. So there's the two exponential decays. What do I know? Here's what I know. They both have a 3 with them. You see they kind of start at 3 also on that. That's the starting value. That starting value only works if they don't add anything in this spot, by the way. You know, it's like sometimes it moves it up and down. But that's where they both start at. So the closer that the base gets to 0, isn't that like the low boundary for exponential decays? Like it's got to be between 0 and the closer it gets to 0, the flatter it's going to be. Which one looks flatter? K or B? Tell your neighbor what you think. Yeah, K is flatter. It goes, I would use a highlighter, K goes down faster. Do you know what I'm saying? Like K really goes down fast. So K is the flat one. That should be this guy. Isn't he closer to 0 in that case for a base? So that means this guy's got to be B. Cool. So let's use that same rationale. Let me erase all this nonsense right here about these exponential growths. The other 3 should be exponential growths. Hey, there's something different about the first one compared to the second 2. What's different about the first one? It's got a 2 in front of it, right? The other 2 have a 3, right? So can you figure out which one has to be the guy with the 2 in front of it? Isn't this kind of like where it, crosses the y-axis, like the starting value on that one? So which one of those crosses at 2? G. Are you with me on that? So that's got to be G. And these other 2, it's all about the base. Whichever one is closer to 1 should be the flatter of those, right? Whichever one is closer to 1 should be the flattest. So which ones are even left? O and R, is that right? Which one seems flatter? R does. So is that the 1.44 or the 1.2? Yeah, and then this one's got to be O. You see how I just kind of problem solve my way through it? That's not the only way to do it. That's just one suggestion. You'll separate them between exponential growth, exponential decay, flatness, and like starting value kind of stuff, right? And then the last thing of the day is just looking at data to see if it's linear or exponential or neither, right? And here's the thing you got to check. You got to check to see that your domain values, been a while, and I'm trying to speed this up, isn't the domain the x's? Do those go up by the same amount every time? 0, 1, 2, 3. Does the domain go up by the same amount every time? Or are they going up by 1s? They don't have to go up by 1s. They could each go up by 5s. You could say like 5, 10, 15, 20, etc. But they got to go up by the same amount. If this is linear data, there is a constant rate of change. If it is exponential data, it has a common factor, like it was getting multiplied by a half every time, or multiplied by 3 every time, or stuff like that. So let's look from here to here. Let's check to see if it's linear. If we just said how much it increased by, what did it increase by from 5 to 10? It went up by 5. Does that happen again? Does it go up by 5? Did it happen again? Did it go up by 5? Didn't it have a constant rate of change of up by 5, up by 5, up by 5? Linear or exponential? Linear. There is a constant change of 5. What if that went down by 5, down by 5, down by 5? You would have to put -5 in that spot. Does that kind of make sense? Cool. Check these guys out. Do those go up by the same amount every time in this data? -1 to 1 to 3 to 5. Like, yes or no? Yeah. Up by 2, up by 2, up by 2. So the domain increases by the same amount. Let's see what happened here. 32 to 16. That went down by 16 if I'm looking at it at linear data. Did it go down by 16 again? Nope. So it is not linear in that case. You don't have to cross it out. I'm just saying it's not linear. There was not a constant rate of change. Let's see if there was like a common factor. If you divided, here's what you got to do. You got to use your calculator and divide second guy by first guy. Second guy by first guy. 16 divided by 32. I get 0.5, right? I got to see if that happens again. If I do third guy divided by second guy, 8 divided by 16, did I get 0.5 again? And if I do fourth guy divided by third guy, 4 divided by 8. Do I get 0.5 again, right? That one visually is pretty easy to see, especially since we've kind of done it already. Didn't go like multiplied by a half, or 0.5 every time. So, but if you didn't turn out to be so obvious, you divide the second one by the third one by the fourth one. So this is exponential. There is a common factor of either 1/2 or 0.5, whatever you want to put. Cool? Please try the number 9 with a neighbor. See if there is any kind of linear change or exponential change, or maybe it's just something else. So these increase by the same amount, so I can try my little test. I'm going to try linear first. You just got to try. You just got to do it and see if it works or doesn't work. So linear, this went up by 2. Did it go up by 2 again? Not linear. Not happening, right? So let's see if it's exponential. Divide. I don't want to roll with the 0, right? Because like dividing by 0 isn't going to work, so I'm just going to kind of skip on this one. Let's do 8 divided by 2. What's 8 divided by 2, baby? That would be a factor of 4 in that case. If you did 20 divided by 8, do you get 4 again? 20 divided by 8. Did I get 4 again? Nope. That's not exponential either because there's no common factor, so that's why it's something else. Are you with me? It didn't go up or down by the same amount, and it didn't have a common factor in that case, so that's going to be something else. And then the last one of them, baby, these increase by the same amount. This one up by 6. That does not go up by 6, so it's not linear. But do they get multiplied by the same amount? 9 divided by 3 is 3. What's 27 divided by 9? 3. 81 divided by 27 is 3, right? So what do you think? That is exponential with a common factor of 3. You could also get a fraction. There could be like a common factor of 1/3 or a common factor of 1/4. But that was kind of a long one, man. I like it.